Hello there. So let's look at some more spectral problems by analysing the infrared spectroscopy and the mass spectroscopy as we try and determine a structural formula. So again, let's just review the different kinds of stretches we get from infrared spectroscopy. Of course, we have the alkenes with that carbon to carbon double bond. The double bond itself usually appears in a moderate strength round about 1680 down to 1640. If there's a hydrogen attached to the double bond, it has a stretching vibration which is moderate to weak, around 3080 to 3020 wave numbers, and also a bending vibration from side to side, somewhere between 1000 and 675, and it tends to be fairly strong, and it also tends to be very broad compared to the majority of peaks. Then the alkynes with that carbon to carbon triple bond. The triple bond itself usually appears somewhere between 2260 to 2100. If the alkyne triple bond is at the beginning of the molecule, then we'll get a carbon to hydrogen bond stretching vibration around 3300 to 3267. That varies in strength. We also have that bending vibration as well for the CH bond, which is attached to the alkyne bond. That's anywhere between 700 to 610 normally. It also tends to be moderate to very strong, and also tends to be very broad, like the bending vibration for the alkene bond. After the alkynes, related are the aromatics with sp2 hybridization around the carbon ring. The carbon to carbon bond itself in the ring sometimes has a peak at about 1600 and often a peak round about 1500, give or take a couple of units, and sometimes a third peak about 1400. Sometimes all of them appear, sometimes only one or two of them appear. Most commonly, the 1600 peak appears, and it's weak to moderate in strength. We often get the CH stretching overtones between 2000 and about 1600. Looks like a kind of bumpy bass line if it's present, but again, it isn't always present for the aromatic. And of course, like the alkynes and alkenes, we have a stretching vibration for the CH bond when it's attached to the aromatic ring, which is above the normal 3000 to 2900 range for an alkane. The sp2 and the sp hybridization has greater S character, so the electrons are held closer to the nucleus and the bond is stiffer. So we see the bond absorbing at a higher energy than normal. So for the CH bond and an aromatic, somewhere between 3100 to 3000, and it tends to be relatively weak in the amount of transmittance. Moving on, we also have, of course, things like the alcohols. Alcohol is very distinctive with that oxygen to hydrogen bond stretch, which is moderate to strong, and it's also very broad, often starting at about 3500 and finishing at about 3000. Looks a little bit like someone put a thumb onto the page and we just drew a line, a curve around their thumbprint. Very distinctive and very broad. We've also got the carbon to oxygen single bond stretch, which will be somewhere between 1200 to 1000. After the alcohols, we have aldehydes and ketones. They have that carbonyl stretch between 1760 to 1670. When present, that tends to be the strongest peak in the spectra, almost 0% of the infrared beam transmitted, almost all of it absorbed. And if it's specifically an aldehyde, not an alkene, then of course we also have that CH bond attached to the functional group. And that gives distinctive stretches at about 2800 and 2700, lower than we'd normally see for an alkane or any other kind of CH stretch. Related to the aldehydes and ketones, we have, of course, the carboxylic acids, which have that OH stretch. It's usually strong and broad, like an alcohol, but it's not as stiff a bond because of the nearby carbonyl group. So it's normally centered about 2900 and starts out somewhere about 3100 and goes down to about 2500. So it's like a big thumbprint that overlaps the CH stretches for the alkane. We'll also see a carbon to oxygen bond single bond stretch somewhere in that normal range of 2060 down to 1000. We also have amines, amines with that nitrogen to hydrogen bond. For a primary amine, it has two of those bonds, so we see two of these stretches in a broad shape together, a little bit like a crab claw, somewhere between 3500 to 3300, and also a nitrogen to hydrogen bond bending vibration, somewhere around 1650 to 1580. That's usually moderate in strength. That sums up most of the main kinds of functionalities we could see. Oops, did I miss one there? Yep. Finally, the nitriles with that carbon to nitrogen bond stretch, and that's usually about 2260 to 2220, usually a little bit further to the left than an alkyne peak, which is in the same kind of region. Because if it's a nitrile, we wouldn't see a CH stretch above 3000. So let's look at some spectra again. And the first thing that grabs my attention when I look at this one is the peak at 3016. That's much stiffer for a CH bond than we normally would see in a hydrocarbon compound, and that immediately suggests to me either an alkyne, an alkene, or an aromatic of some kind. Now we can rule out the alkyne, because if that was true, we would see a peak in the 2200 range to 2100, a moderate to weak peak. For the triple bond itself, we're not seeing that here. That would be about here in the spectra, and it's pretty much baseline blank. So we can rule out the alkyne. Plus, of course, the CH stretch isn't far enough to the left. It should really be about 3300, not in the 3000 range. We can also rule out the aromatic. Although the CH is in the right range, we would expect to see a moderate to strong peak about 1600 and another one about 1500. This peak here is really just bending vibrations for an alkane CH bond, not what we're looking for. And then the clincher for the alkene, as well as having that peak at 1660 for the carbon-to-carbon double bond itself, is that broad and moderate to strong peak in the 1000 to 600 range, which is for the bending vibration of the CH bond, which is attached to the alkene. So CH stretch, the carbon-to-carbon bond stretch, and the CH bending vibration. We look at the mass spectroscopy. We've got the molecular ion peak at 70 units. We can divide that by 14, which is the mass for one CH2 unit. Normally it's a 1 to 2 ratio for carbon and hydrogen. And that comes out 5 times neatly to give us 70 units. So C5H10. That fits our expectations for an alkene, which has a general formula of CnH2n. Our hydrogen count is down by 2 compared to normal saturation for a hydrocarbon with 5 carbons. Full saturation, of course, for the alkane, pentane, would be C5H12. So it's a reasonable guess to suggest that it's pent2ene with the carbon-to-carbon double bond between carbon 2 and carbon 3. If we look at some of the main peaks from the mass spectroscopy, that would seem to be backed up. because they peak at 55, which suggests that we have alpha cleavage on the left-hand side, leaving us with 55 units of mass. And then the peak at 41, suggesting we have alpha cleavage on the right-hand side, therefore giving us a peak at 41 units of mass. So that looks as if it's fairly conclusive for the pentuene. Looking at the next one, we have got a couple of peaks which we have highlighted again, the main peaks for the functional groups. And the main thing that catches my eye is that 1711 peak, which is right in the range for a carbonyl group, as I tried to say. So that peak itself suggests maybe it's a ketone embedded somewhere in the middle of the molecule. Maybe it's an aldehyde with the carbonyl group right at the beginning, or maybe it's a carboxylic acid. So as we look at those peaks, we could rule out the ketone itself, because a ketone wouldn't be expected to give this broad peak at 2964. Mind you, neither would the aldehyde be expected to give a peak in that range. So we're really left with a carboxylic acid. That broad peak centered about 2900, starting in the 3000s and going down to about 2500. It looks like it's the OH stretch for the carboxylic acid. I've outlined it in red here, so you can see how it's overlapping with the CH stretches of the alkane part of the molecule. Big and broad, just like an alcohol, but further to the right. So that's our OH stretch. Then the 1711, as we've already said, the carbonyl stretch itself. And then our peak at 1213 is the carbon to oxygen single bond stretch. So as we look at the molar mass, 116 from the mass spectroscopy, we of course can account for two oxygens, the carbonyl oxygen and the OH oxygen. So we need to subtract 32 units from the mass. That leaves us with 84 units. Now that we can divide by 14, because now it's just carbon and hydrogen, to tell us the relative number of CH2 units. That comes neatly 6 times over. So it looks like C6H12. Add in the oxygens, which we'd taken into account. It gives us a formula of C6H12O2. That strongly suggests that we've got hexanoic acid, or some kind of constitutional isomer derivative. Now, it looks like the mass spectroscopy is backing up this idea and confirming hexanoic acid specifically. If we look at some of the other peaks, that peak at 73 looks as if the bottom end, the tail end of the molecule, has dropped off, leaving us with the functional head. And the next peak at the 60, our main peak for the spectra, would suggest that we've got a McLafferty rearrangement. So if we reimagine the molecule curling around itself a little bit, we can imagine the hydrogen coming off the carbon here, the oxygen using those pi electrons to pick up the hydrogen, the carbon to hydrogen bond would break, and the electrons would swing round to make a new carbon to carbon bond. That would then cause the adjacent bond to break, and so we'd end up with these rearranged fragments which would have broken off, and the carboxylic acid head group rearranged would give that mass of 60, and the tail end would give that mass of 56, which we also see in the spectra. Let's look at a third and final one.